Good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. 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 Most wonderful good afternoon, everybody. Good afternoon.
I'll see you next week. Have a good week.
I already wished you a good afternoon, so good afternoon. 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 Good afternoon.
Guten Tag, Herr Klappe. Wie geht es dir?
Danke, sehr gut.
Yeah, cool.
Und
As
Ihnen?
much as I know.
Fair
I
enough.
only started learning German
Oh,
recently.
no, very well.
I wanted to ask, would you have time to maybe talk at the end of this lecture? Just
About
maybe briefly. I guess if I had to surmise it, I had some ideas. I'm writing a book about something. I guess sort of maybe not getting into it too much. Maybe about the student experience as it relates to a few other things. I've been
sounds
speaking
good.
to
Sounds good.
Richard
Let's
Williamson
talk.
about it. And I thought I'd like to.
Yeah, let's talk about it.
Cheers, thank you.
Would be great.
Morning.
Good afternoon. It's afternoon. But it's all right. Careful. Oh, good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Careful. Traffic. Good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Careful traffic. Good afternoon. Now it's safe.
Thank you. Thank you.
Good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon again. Good afternoon. Good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Good afternoon.
Because we're taking Emily out, we thought we ought to do something.
I see a ballet of Dracula at there.
You are?
I did. It was really good.
Good afternoon. Most wonderful good afternoon. Good afternoon. Most wonderful good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Oh, is that?
I don't have time for lunch.
Huh?
I hope you don't mind.
I don't care.
I
What
didn't
is
have
it?
time for lunch. It's just beans and
Beans. Oh no.
Yeah, he's a vegan.
I'm a vegan.
So it's all he eats.
No, 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 no,
beans
no.
and
I mean,
tattoos.
beans that has catastrophic effects.
Oh yeah, maybe
On
I
the-
don't
I eat
sit
enough
near
with
you.
them.
On the
Maybe I don't
trousers.
sit near you.
No, I'm
On the
used to it, it's
trousers.
fine.
Huh? So you don't eat chocolate?
I do if it's vegan.
Okay.
How much chocolate can you eat before you feel sick?
Okay, let's get started. Most wonderful good afternoon, ladies and jelly beans. Lovely to see you on a Friday afternoon. I don't think I can't take it for granted that you come in. So it's very nice to see you. So what we are going to do today is we will elaborate a little bit on what we did yesterday with reaction kinetics. We will discuss special cases, zero, first, and second order reactions. And then we also will discuss something special about first order reactions, namely half-life. And hopefully we will be able to address the question, how much chocolate can you eat before you feel really sick? And if it doesn't make sense, don't you worry. We hopefully everything will be revealed. So what we did yesterday is we discussed very briefly the general rate law equation. So if we have, for example, a reactant A, and this is consumed in a reaction, and I abbreviate it like that just with an arrow to indicate that this is consumed. We said we can write the general rate law for that as dA, a very small change in the concentration of A within a very small time period, and this D basically indicates that these are almost infinite small changes that we are looking at. And the general rate law for that rate, dA over dt, is, since we have a consumption of A, it's a negative sign here, so negative K times, and K is the rate constant, K times the concentration of A to the power of M. And as I said, K is the rate constant. A rate constant is always positive. There's no exception to that. And M simply denotes the order of the reaction. The order of the reaction, as we discussed yesterday at length, just simply is a mathematical concept. It doesn't have any kind of physical connotation to it. The order is just something to make this equation work, basically. If we are thinking about how many molecules or entities have to bump into each other, we would express that with the word molecularity. tells us how many molecules need to bump into each other. The order of a reaction only is a mathematical concept. And the order can be basically any number that you can think of. It can be a negative number, it can be a positive number, it can be a fraction, it can be zero, it can be whatever you want. So that's quite important for you to remember. And I showed you that if we want to determine this rate order, there is a nice trick to do that. All you need to do is you basically say, I don't care about whether it's a consumption or not. I just simply write the rate of the reaction. Rate equals K times A to the power of M. And then I can just simply take both sides log. And the nice thing is, actually, you can use whatever log you want. You can use log to the base of 10. You can use the natural log, so base of E, 2.718. You can use log to the base of 348,556 if you are so inclined. Doesn't make sense, but if you want to, you can do it. Yeah? And it works. Works for any kind of log, so you don't have to worry about that. So you get log rate equals M times log concentration of A plus log rate constant. Just write it in the right form. And we said that is the equation of a straight line. And therefore, what we could do is we could easily plot that. So we can plot log of the concentration of A versus log rate versus log concentration of A. And ideally, we should get a straight line. This point here, that would be the intercept, and that is log K. And the gradient of that, that would be our rate order M. And I think that is where we left it yesterday. So what I want to do today is, as I said, I want to discuss some special cases, because these are fairly common cases that we will encounter, and I will give you examples for them. One of these cases is the elimination of alcohol from the bloodstream. So we have alcohol, and that is eliminated. And we are looking at a special case. We are looking at the alcohol elimination in men. Why not women? It looks like that women are more complex. And you can argue, yeah, we always knew it. Women are more complex, yeah. There are sort of a couple of truths in life. Why women are more complex. Women are more intelligent than men. Is that right? And the third fundamental truth is Earth is flat. Anyway, alcohol elimination in men. And in order to give you an idea what I'm talking about, I'm not going down the route of alcohol, I'm going down the route of chocolates. Let us pretend I've got a box with 100 chocolates here. So I have a starting point, 100 chocolates. And let's say I can eat 10 in 10 minutes. Okay? So how many chocolates do I have left after, let's say, after 50 minutes? How many chocolates have I got left? 50? Is she right? How did you do that? You don't like chocolate?
No, I do like chocolate. I was just surprised that I bought it.
Me too. I'm very grateful that you're sitting that close. You know, usually it's somebody up there, and either I have to run up there or I have to throw it, and more often than not, I hit the wrong person. How did you do it? Oh, you did the 10, 10, 10, 10 step. Is that right?
Well, it's just how do you get from 10 minutes to 50 minutes times by 5 and times the 10 by 5, so you've got 50 and then times the minus 50.
You deserve that chocolate. Let's just simply go step by step. So we start with 100 minus 10, so that's the first 10 minutes. We've got 90, right? Minus 10, that's the next 10. We've got 80. Minus 10 gives us 70. Minus 10 gives us 60. Minus 10, and that gives us 50. You're absolutely right. So we have 50 chocolates left after 50 minutes. Now, of course, imagine it's not that convenient, the time scale. Imagine we have, concentrations to deal with, and it's awkward. Well, it would be nice to have a sort of almost like an equation for that. Right? So, what we can do is, actually, we can say we can put that into our general rate equation. So dA over dt, that's the rate equation. In this case, it's chocolate. Plus or minus? Does the chocolate get consumed? Is the Pope Catholic? Does a bear in the woods? Yes. Of course, the chocolate gets consumed, so it is a minus. Minus K. That's the rate constant at which we eat. Times. Now, here's the question. Does our rate at which I pretend I can eat the chocolate, does that depend on how much chocolate is there at the beginning? If I say I can eat 10 chocolates per 10 minutes, do you know how much chocolate is present at the beginning? Does it matter whether, I've 1,000, I've got 100, I've got 200? Does it matter? The rate doesn't care about that. It's a constant rate, 10 per 10 minutes, right? So I can write this as the concentration of A, or the concentration of chocolates, to the power of 0. What happens to anything power of 0? What is that? 1. So I can also write this minus k times 1. And 1 I don't write usually. Yeah? Or just times 1. Let's just write it like that, just to remind ourselves. So, what does this say? It says the rate is a constant. And the rate does not depend on how much chocolate is there. Yeah? This is a zero-order reaction. And of course, we would like to do something with it that we can sort of almost do a little bit of maths with it. How much chocolate would be left if I say I can eat 2 3/4 chocolates in 25 seconds? How much chocolate would be left after 12 minutes? Now you run into problems, right? Because that's not that easy to calculate with the stuff. So it would be nice to develop a sort of an equation for that. And actually we can do that. Let's write this down. dA over dt equals minus constant. Now, for those of you who have done that at school, at Maths A level, the left-hand side, dA over dt, the way I say it, already indicates what kind of equation is this. Does anyone know? What kind of equation is that? dA over dt, when I say it like that.
I'm thinking back to A-level.
You're thinking what?
I'm thinking back to A-level maths. Can I remember this?
Ah, okay. Let's wind back. A-level maths. What kind of equation is that? Loud. Say it loud. It's a differential equation. And differential equations are a pain. Usually you can't solve them. But because it's Friday and you are with me, we can solve this equation. I'll show you the trick for that, how you solve an equation like that. What you do is, a differential equation always goes with something very small divided by something other small, dA over dt. And what you do for a differential equation, you separate what is called separate the variables. So you bring everything with a on one side and everything without a to the other side. So we just bring that to the other side, and we have dA equals minus k times dt. And now you might argue, Master, now what? Right? Now, what is the opposite, what is the inverse mathematical operation to differentiation? It's integration. Exactly. So what we can do is, we can now integrate both sides of this equation. And the integral sign is this lovely sort of, it looks like an S, which, for those of you who have done integration, makes sense because integration is nothing else but a summation of something. So we can integrate integral of dA equals minus k times integral dt. I'm not writing down the conditions because at the end of the day, you don't need this. You don't need this, how I get to it, because I will give you the equation that you get from this integration. And we basically say the integration goes from a time point t equals starting point, and I sometimes write that as ti. This means initial time or start time to a time point where I want to observe it. And I usually abbreviate that with TF, which means final time, or the time where I want to observe. So for example, how many chocolates do I have left after 20 minutes? TF would be 20, TI would be, well, when I start, that would be basically 0. Yep? Now, the solution to this integral is my final concentration minus my initial concentration equals minus k times T final minus T initial. That is basically what you get when you try to solve this integral. If you start hyperventilating with the integration, yeah, and I can see some people who look slightly worried. As I said, you don't need to know it. You don't need to know how to do it. What you need to know is that for a zero-order reaction, it is this equation that you need to know. So, coming back to our example with the chocolates, I can say my A final, oh actually that is what I'm looking for. A final, that is what I don't know. My A initial, my starting concentration, that was 100 chocolates. My rate constant was, what did I say, 10 chocolates per 10 minutes. My T final, that was 50 minutes. And my starting point, well, that was the starting point. There was sort of, we can set that to 0, basically. 0 minutes. And I can very easily rearrange this equation. So I just bring that to the other side, and I get a final, and I just, with your permission, I just write it as AF equals minus K times, let's write it with the proper numbers, minus k 10 over 10 chocolates per 10 minutes times 50 minutes minus 0 minutes. Well, that gives me 10 over 10, that's 1. 50 minus 0 is 50, so that gives me 50 chocolates. The minutes cancels out. Well, I've got chocolates, 50 chocolates. That makes sense to you? How can we actually represent that? A final equals minus k times t plus a initial. Well, if you look at that, and for the t, that is just because I just don't count the t initial. That's always 0 in our example here. If you look at that, this actually is nothing else but the equation of a straight line again. So if I plot concentration of A over time, what I will get is a straight line. Does that make sense? And what you see is basically my concentration of A, my chocolates, get less and less and less. The amount of chocolate goes down quite nicely. And it's constant. It goes down constantly. 10 per 10 minutes. Make sense?
That bit does.
Sorry?
That bit does.
That bit does. Good. Just look at that. So this point here, that is our initial concentration, AI. The gradient of that, what is the gradient? It's the rate constant, that is K. Note, K is positive, but because we have a negative sign, it has to go down. Now, what happens if we hit 0 here? Can the graph go into the negative range? No. Why not? You're absolutely right. Why can't it go into
Once your concentrations are gone, once there's nothing left.
once I've eaten the chocolate, right? There's no chocolate left. So we would express this as just simply something like that. Probably should use a different color. And when it goes to 0, that's it. No chocolate left. What have I got left? An increased risk for diabetes. At least if you eat all of those. Does it make sense? Yeah? So the important equation here is, let me write that down again. A final minus A initial equals negative K T T final minus T initial. Happy with that? That is a zero-order reaction. Examples for a zero-order reaction, as I said, is of alcohol from the body of a woman, of a male, sorry, not a woman, of a male. Elimination of alcohol usually from female body follows a different rate order. Why? We are not entirely sure why this is. It has something to do with probably some enzymes in the liver that are involved in the detoxification of alcohol. Exactly how does it work? Not sure. Many drugs are eliminated by a zero-order reaction. And as we will see next year, enzymes also work at a zero order when they are fully loaded with substrate. Then an enzyme works in the zero order range. So zero order reactions are really important, and they are really easy to deal with if you remember this equation. Yeah? And I expect you to remember this equation. Right, so that was our first special rate order. Now let's have a look at another one, right? Let's say I've got my 100 chocolates, and again I have this one here. I've got 100 chocolates, and now my claim is I can eat 10% in 10 minutes. There's only a slight difference to what I said before. Before I said I can eat 10 in 10 minutes. Now I say I eat 10% in 10 minutes. There's a slight difference. How much chocolate have I got left after 50 minutes? Now you have to do the finger thing, right? Sorry? Is it 50? No? Is he right? No.
Is it because it would not curve, because it's not constant anymore?
Ah, loud?
Or it wouldn't be a constant anymore, it would be like a curved...
It will be curved. Now you're getting close. And I keep my chocolate. No, actually. Okay. If you're planning to become England cricket captain, think about your career choices. If you can't catch that easy. Right, let's try to figure it out, okay? So, we start with 100. 10% of 100 is 10. So that's our first 10 minutes. How much have we got left? 90. Next one, 10%. 10% of 90 is 9. So we've got left 81. 10% of 81 is, we can't have fraction chocolates, right? So we have to round. 10% of 81 is 8. How many have we got left? 73. 10% of 73, 7. How many have we got left? 67. 10% of 67, we have to round, again is 7. How many have we got left? 60. So if we plot that, A, concentration of A versus time, we would probably find something like that. And you're absolutely right, it's curved. Why? It is because we have this 10% in it. So the rate, in this case, depends actually on how much chocolate we have left at each step. That's completely different to before, where we had the 0. It wasn't dependent on how much chocolate we had left. So let's try to write this in an equation. dA over dt equals, of course we consume chocolate again, minus k times and now it comes. Concentration of A to the power of 1. This basically tells us that the rate depends on how much chocolate we have at each step. That is what this equation tells us. And as you see here, the rate order is 1. And therefore, we call that a first order reaction. Does that make sense? Now, of course, instead of doing the counting thing, it would be lovely to have an equation for that, wouldn't it? So let's try to do the same thing with the integration. We bring the dt to that side, and we bring a to the other side. And we have dA over A equals minus k times dt. We've separated the variables. And we integrate both sides. We get integral of dA over A equals minus k times integral dt. Actually, the right-hand side, that's absolutely trivial because we have done that before. We have done the equation for that. That is just simply equals minus k times t final minus t initial. Done it before for the 0 order. That's easy. But on the left-hand side, that's a bit tricky. Does anyone know what the integral of dA over A is? what's the stem function for that? This is going ln? You're absolutely right. This is going to blow your mind. And if it does not blow your mind, then you have no emotions, right? Because this is cool, this is sexy, this is, you know, it is just, whoa, where does that come from? You know? You are absolutely right. Actually, I think, or did you just Google that? You even get choice. The function for dA over dt is an ln. And we have ln of A final minus ln of A initial, our starting concentration, equals minus K times T final minus T initial. And this is the function for a first order reaction. And I want you to remember this equation. Where do we find first order reactions? Many processes in the cell follow a first order reaction. Also in your body, elimination of many drugs follow a first order reaction. And whenever you have anything to do with radioactivity, follows a radioactive decay follows a first order reaction. So, really nice example, radioactive decay. That follows first order reaction. Now let's see, what does that look like, this weird thing with the LNs and stuff like that? First of all, what we can do is we can rearrange that equation. We just bring that to the other side. And instead of T final minus T initial is 0 again, usually. We write this as ln A final equals minus K times T plus ln A initial. And you've probably tweaked it the way I've written it. Lo and behold, can you see it? What is it? It is the equation, you're absolutely right, for a straight line. Y equals mx plus c. But just in this case, we simply don't plot A final versus time. We plot ln of A. So let's plot that. We plot ln A versus time. And we get a straight line. Our intercept here is, what is the intercept? what is this point here that I indicated? What is the intercept? What do you think? It is, you're absolutely right, ln AI. You can't catch. Oh. You're welcome. This point is ln AI. ln AI. It's not AI, it's ln, right? What's the gradient? It's again the rate constant. Can this graph go into the negative range? Yes? Are you sure?
Yes, you can have ln A being something negative without A being negative.
Spot on. Spot on. It can be negative because, as you rightly say, we can have ln A can be a negative number. A can't be a negative number. Negative concentration wouldn't make any sense. But ln A can be a negative number. Get another one. But I don't want you to, get sick. Mind you, 2 is all right. Does that make sense? No? Right, let's have a look. The graph is okay. Yeah? So if you have, for example, ln A ln A and A excuse me, A equals 0.1 molar. What would be ln A in this case? Get your calculators out. ln, negative logarithm, ln. So ln 0.1 would be negative 2.3. Negative 2.3. That means it can go into the negative range. Yeah? What would be ln minus 0.1? Try that on your calculators. What gives ln minus 0.1? What does it give?
I don't like it.
You don't like it?
No, it doesn't like it.
Oh, the computer, the calculator doesn't like it. Sorry, what? No? You can't take the ln of a negative number, right? But an ln of a number can be negative. Make sense? Fantastic. So, we have done that. Now, I would suggest we have a 7-minute break before we go then into a little bit more of that. I tell you a little bit about the units and things that we can do with this equation. Okay? 7 minutes back, and then we carry on.
Sorry, I didn't want to get out because I'm sort of hemmed in. But I was wondering, I was a bit confused about one thing, going off of the chocolate analogy you used before. That makes sense that you would be limited at 0 because you run out of chocolate. What's special about radioactive decay then, where you could have, like at least using the same principles, you could have like a negative amount of like an isotope or something? Am I misunderstanding?
No, you can't. We will discuss that in a minute.
Okay. Alright. Because I was confused about that because I thought
We will discuss that in a minute.
Okay. Alright.
Yeah? It's not with chocolate where it goes constant down.
Yeah.
Again, what you have with a radioactive decay or with any first order reaction is after a certain time point, you have 50% left. Percent.
Yeah.
Right? After the next time point, again you have 50% of the 50% left. The next time point, you have 50% of the 50% of the 50% left.
So it halves, but would it still not just tend to 0 though?
I don't think anyone.
It will converge to 0, but it will never reach it.
I think I've done it.
Because you would only get half every time. But that makes sense. But then how, in that case, why is it constant and why does it go past 0? Yeah.
Ln.
Okay. So it's logarithmic.
Yeah. So you can have this half, you can have this half of half of half.
Yeah.
It's still something, but it would be negative. Ln would be negative. A would not be negative.
Oh, I see. Okay. That makes sense to me.
Make sense?
Yes, I think so.
But we will discuss that because it's not. You are not the only one with that question.
Oh, okay, that makes sense. That's good to know.
Was it you who said you did engineering?
Yeah. It was here at Kent.
All right.
But it's funny, I would say I didn't really learn a lot. I think most of what I know of maths was probably self-taught. I was quite maths illiterate when I came here. I was studying biosciences before I came here.
Oh, really? Here?
Yeah, before I came to Kent, and then my dad tried to convince me to do engineering. He convinced me to do engineering, so I had to join the foundation program and learn all the maths and physics. Around first year, I basically stopped, so my knowledge of maths, sorry.
Little request, could you call it a natural log? Because when I lip read, then N looks exactly the same as LN.
When you what?
Lip read.
Lip read.
Yeah.
Natural log.
Log.
I will try. Yes.
Yeah. Like, it's okay because you write it down.
Yeah.
But I keep getting confused because.
Okay, natural log.
Yeah.
I will try my very best.
Yeah.
It could very well be that occasionally I slip up on
it's
it.
not a big deal
but
because normally I can work it out.
Yeah.
But it's just a little bit inconvenient
I will
for
do
my
that.
deaf ears.
Yep, I will do that. Good. And when you did the engineering, did you do?
Yeah, so it was funny because I suppose that the context in which I learned a lot of this maths was very specific to engineering. So it's interesting trying to connect the two and kind of having like a broader perspective of the maths. It's quite interesting.
Good. And I'm not boring.
No, I find it interesting.
So I just wanted to ask, in the last lecture you were talking about if the order is like a complex number. So that would also mean that the rate would be a function of a complex number, right? I was just thinking of that.
About
So because if it's an exponential distribution, then you get it as a function of a complex number, the rate?
you would. What we are doing is special cases. but there are ways how you can integrate the equation if you have sort of a to the power of m, and m is not 1.
What have you been able to
Then you can, there are tricks to integrate.
like,
Yeah, but you were talking
I
about
can believe you
how
do something like that. It sounds
Oh, you
it
mean,
can be a complex number. The order can be a complex number.
do you mean complex number or imaginary? Oh, imaginary.
Because if it's an imaginary, so it would just be an imaginary. It wouldn't be truly complex.
I have no idea how you would do that.
Excellent question.
But so that would also indicate that the rate then would be a function of a complex number.
Of an imaginary number. But so far, nobody has educated me whether it can even be an imaginary number in the rate constant, in the rate equation. So I have no idea.
And so what would it mean if it was irrational?
If it was irrational, it just is a number. So if, for example,
molecules or anything,
no, it has nothing to do with molecules. It just indicates by what number you need to put it to the power to make this equation true. Yeah?
Oh, it's all like. Because I've been sick for ages. This is my first time home. Sort of like touching your toes, it's like a good sort of like almost like feeling like contracted by
Why do you always make the break 7 minutes long? Is it because 5 minutes is too short and 10 is too long?
Indeed. Make sense?
breaks be 7.5 minutes?
Sorry?
Under that logic, shouldn't the breaks be 7.5 minutes?
Why?
'Cause
For
if
the
you're gonna go
cigarette.
No, if you're going in the middle of 10 and 5, the perfect middle would be
That's,
7.5.
no,
I feel
no,
like
no,
we're
no,
a
no.
man
No, that would be OCD.
That's, maybe that's just me then.
Yes, of course.
So with this,
Protein, huh? Are you going to
With
chase
that-
lions, Taru? Do not eat.
with that, so that's the reaction equation. Yeah. So do I need to know how you get from that to that? Because I don't get this like integral.
Don't worry about the integration.
I don't need to worry about it.
Alex, don't worry about it.
It's a beautiful, beautiful. Calculus is amazing.
I'm alright actually.
Yeah, no, I love calculus. Calculus is it's just, oh.
Don't worry about it. You need to know this equation, and
Which one's that?
that's the first order reaction, ln.
That's first order.
Yeah?
So with the other thing, so zero order, that's
Yeah.
when if you increase the concentration, it doesn't affect the rate.
Bingo.
First order, if you double the concentration, it doubles the rate.
Bingo.
So what? Second, it quadruples.
Bingo.
So third, it times this by 9.
Nines.
So what if it times this by 3? Is that like 1.5 order?
It's just like, we use it as a ratio, right? So you base it from the zero.
We will do that next week.
So if your first would be...
So we've kind of done this at like A-level chemistry.
Sorry?
So this is kind of like A-level chemistry.
Exactly.
Yeah.
You've done that in A-level chemistry.
Yeah.
I didn't
This
know
one.
so I
I
haven't done
did.
this, but-
You did. So you shouldn't have any problems with that.
No, it's not like a
Good. Okay, let's carry on. Let's carry on. Because today is your lucky day. You don't get just one equation for the first order. Bog off. Buy one, get one free. No, even better, buy one, get two free. What is he talking about? This is the equation that we just derived, yeah? But then sometimes it's really inconvenient because we don't give a flying flamingo about ln AF. We want to know what AF is, not ln AF, right? So we can rearrange these things a little bit. First of all, under the rules of logarithm, we can combine this side here. And we can write this as natural logarithm ln of AF divided by A initial. It's exactly the same stuff. A minus in ln becomes divided. Equals minus k times tf minus t initial. Does that make sense? And if we want to get rid of the ln altogether, what do we need to do? Of the natural logarithm, what do we need to do? Beautiful. We e both sides, and we get e of natural log AF over AI equals e to the power of minus k times t final minus t initial. E and ln eliminate each other, and we have a final over a initial equals e to the power of minus k times t final minus t initial. Or, if you want AF, you just bring that to the other side, and you have concentration of AF equals A initial times e to the minus k times T final minus T initial. How cool is that? You get so many equations and you only pay £9,250 for that. Isn't that great? Ha, a bargain. It's a steal. Right? Now, the good thing is you don't need to remember all these equations, because if you remember only this equation, and you can do your ln's or natural logarithms or whatever logarithm rules, then the rest just simply follows. If you can't do it, then you have to remember this equation, and you probably have to remember this equation as well, and you probably have to remember this equation. So now is a good time to learn the rules of logarithm, because it makes life so much easier. Right. Now, just for a little bit of fun, as much fun as you can have with that stuff, without being a masochist. What happens if our A final is half of our A initial? How long does it actually take from, say, going from 100 chocolates to 50 chocolates? How long does it take? So let's see. Do we have a good equation here? Yes, we have. We want to go from 100 to 50. Let's take this equation here and see if we can figure out our time span, our TF minus TI. So let me write that down again. ln A final over AI equals minus k times T F over Ti, minus Ti. So let's figure out how long this time span is. T final minus Ti. And all I need to do is I bring that to the other side, and I get my T, the time span, equals natural log A final over A initial divided by minus K. Now, let's put in numbers. I said my final A, that's 50 chocolates. So natural log of 50, initial is 100. Divided by minus K. What is 50 over 100? 0.5, huh? So we have T equals ln 0.5 over minus K. And according to the rules of logarithm, I can do something quite nifty. I can write natural logarithm of 0.5 divided by a negative number is the same as natural logarithm of 2 of 100 over 50 divided by k. Can somebody please do the honors and put into their calculator ln2? And let's see if you are faster than me. 0.693. Thank you. 0.693 over k. So that's the time span. How long it takes to go from 100 chocolate to 50 chocolates. 0.693 divided by k. Okay. Now, let's do a similar thing. Let's say we go from 50 to 25 chocolates. How long does that take? T equals natural log of 25 over 50 divided by minus k equals, and I'll do it the other way round, equals ln 50 over 25 divided by k. So how long does it take to go from 50 to 25? You say it is 0.693 over k. Oh, wait a moment. Whoa. Hold your horses, right? Because we just said that is the time it takes to go from 100 to 50. And now you are trying to sell me that is the same time as going from 50 to 25. Isn't that weird? You are right. It's the same time. Halving it is always 0.693 divided by k. So how long, if you have to hazard a guess, how long does it take to go from 25 to 12.5? 0.693 divided by k. And because of this beautiful relationship, this t has a special name. This t is called half-life. Half-life t, and very often it is abbreviated as t subscript half. Please, in an exam, write down half-life, not low-life. I have seen that in some exam papers. It's not a low-life. You are a low-life if you convert a half-life into a low-life. That's totally illegal. Half-life of a reaction equals ln2 over k. But this relationship is only true, without any exception, this relationship is only true for a first-order reaction. If you have any other reaction, writing down a half-life does not make sense at all. You can even go so far and say, he has put down in the exam paper there's a half-life, I know this must be a first order reaction. There's no other way. Half-life, first order. Now, what does that actually mean? If we plot our concentration of A versus time, and we get something like that. This is our starting concentration, AI. This is AI half. So this is one half-life. Now, this one here, this point here, is AI half, a quarter of AI, of the initial one. Again, this is another half-life. This point here, 1/8. Another half-life. It's not drawn really nicely, but all the half-lives are the same. Let's have a look at, for example, a radioactive element. Let's say we start with 1,000 atoms of a radioactive element. After a half-life, how many have I got left? 500. After another half-life, I've got 250. After another, I've got 125. After another, I have got, and so on and so forth. Now, that wasn't a particularly good example, because with a limited amount of, let's say, atoms, you will come to a point where you have 2 atoms left, and then after a half-life, you've got 1 left, and then by definition, atoms are no longer dividable, things like that, so it would stop. But in theory, a first-order reaction thing would never reach 0. If it was, for example, a concentration, it would go down half, 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 half. You got the gist? Half, half. It would go towards 0, but it will never reach 0. Does that answer your question? Yeah? It will never reach 0. Now, usually when we are dealing with radioactive decay, and that's not just something really esoteric, I will give you an example in a minute. When we are dealing with radioactive decay, we are not usually working with rate constants, because rate constants are a little bit awkward. Instead, what people usually work with is half-lives. So, for example, the isotope 32 phosphorus has a half-life of 14 days. Now, can we do any calculations with that? Yes, we can, because we know that the half-life of a reaction is ln2 over k. And with that, I can easily calculate k. I just have to rearrange this equation and say k equals 0.693 divided by 14 days. And with that, I can, with this relationship between the natural logarithm 2 divided by k and half-life, I can convert a half-life into a rate constant and the other way around. Make sense? Richard goes like that, yes, so great, good. Let's have a quick look at units. You know, I have this fetish about units. It's important. Everything has to have some order, has to have some units. Let's have a look. What is the unit for a first order rate constant? What is the unit for k in this case? 0.693 doesn't have a unit, but we have the unit time in the denominator. So here the unit for k would be 1 over time, or time to the minus 1. That's a typical, that is the unit for a first order rate constant. Oh, by the way, when I said first order reactions, drug elimination, radioactivity, next term we will discover that enzymes also operate under first order reactions. I told you earlier they operate under zero order, and it's not just because I can't decide whether it's zero order or first order. Enzymes, as I told you yesterday, are such absolutely horrendous buggers that they basically do whatever they want. So they can do zero order and first order, and anything in between, which makes them so interesting and fascinating. And I love them. Okay, so that's k. Now, let's see how we can come up with units in a more general way. We just simply say we have our rate equation, so dA over dt equals minus k times t. And let's just simply do a unit equation. So what's the unit for this A if we are looking at concentrations? Molar, yeah? So we have, oh, sorry. I should write it like K times A. I should write it like that. So we have molar unit for T, minutes, time, yeah, equals K times, what's the unit for this A? We just said molar, so molar cancels out. K equals 1 over minute, 1 over time. So unit for first order reaction is 1 over time. Now, dA over dt equals minus k. What kind of reaction is that? It's a zero order, absolutely right, because it doesn't depend on A. You can throw in as much A as you like, the rate doesn't change. It does not matter whether there is A or how much A, it just simply doesn't change. So what is the unit for K in a zero order reaction? Loud? You are absolutely right. The unit for K in general terms would be, let's say, concentration over time. Or, as you said, for example, molar per minute. So, by just simply looking at the units of a rate constant, I can immediately twig, hey, that's a first order or zero order reaction. Simples. Can do that. Very easy. Don't have to do complicated things. That make sense? Tell you what. Because it's Friday, and you have been so good, we do another reaction. Yeah, shall we? Yeah, let's do it quickly. Hey, cool. Let's do the following reaction. A plus A. It's another very common reaction that you might find. We can write that as dA over dt equals minus K times A to the power of 2. Now, big guess for you guys. What do you think we would call a reaction that follows this scheme? Second order. Brilliant. As my famous friend and even more famous great American philosopher once said, her name is Britney Spears, it's not rocket surgery. It's a second order reaction. Absolutely right. So, how do we deal with that? Well, we integrate again and set Alex into hyperdrive with the integration. But again, you don't have to worry about that, because the equation for that, when you integrate it, is this time 1 over A final minus 1 over A initial equals, and that is Sott's law, positive K times T final minus T initial. Where the positives and the 1 overs come from, don't worry, right? It's not terribly important in this case. That's just simply the equation. And the way you would plot that would be On the x-axis, you plot time. And on the y-axis this time, what do you think you plot on the y-axis? Creative ideas, please. Shout out.
Would it not just be 1 over A?
Absolutely. We would just plot 1 over A. And what would we get? Would the graph go down or up? It would go up, exactly. So it would start here at that point, and it would go up. And that point would be 1 over A initial. The gradient would be our rate constant. And the unit for K would be concentration to the power of -1, time to the power of -1. Again, you can see from the rate constant, from the unit, you can immediately say, if it has this unit, we know it must be a second order reaction. Now, sometimes you collect data. You just simply measure concentrations and, or rather, you measure, you have time, and you measure concentration of a substance. So 0, 1, 2, 5, 10, time in minutes, and the concentration in, let's say, millimolar. And you get some data for that. By the way, this is a very common exam question. Here is time, and there is the concentration of your substance. And now I want you to figure out what order is this reaction. How can we do that? Well, we know that from this session today, we know if we plot concentration versus time, and it goes down like that. Concentration versus time, and it goes down in a straight line. What order is that? Loud? It's a zero order reaction. Fantastic. Can it be a first order? Can it be a first order reaction? Definitely not. Thank you very much for saying no, because otherwise I get seasick. It has to be a first order. If it's a straight line, if you plot concentration versus time, it must be zero order. Okay. Now we have the same scenario. We have time, concentration, and you plot it, concentration versus time, and you see something like that. Can this be a zero order? No, can't be a zero order, because you know that when you plot it like that, it has to be a straight line. This is not a straight line, unless, you know, I've got some issues with my eyesight. So it can't be a zero order. Could it be a first order? It could be a first order, yeah, because we know that it goes down like that. So what can we do to see whether it's a first order? Well, instead of plotting concentration versus time, we just simply plot Ln concentration versus time. Ln concentration versus time. Hey, look at that. It gives us a straight line. Nice straight line. This means if we plot Ln versus time, and it gives a straight line, must be a first order reaction. Can't be anything else. Can't be a zero order, can't be a second order, can't be an in-between order, must be a first order. So, I've plotted Ln concentration versus time, and I still get something like that. Sir, what's wrong? Well, nothing's wrong. Just tells you it's not a first order. Could be a second order. So let's see. We get time, concentration. We plot concentration versus time. We get something weird like that. We plot Ln concentration versus time. We still get something like that. We plot 1 over concentration versus time. Oi, cool. Look. Hey. Wow. Straight line. We know this is a second order reaction. Now, in an exam, should I, be so inclined and give you a question on kinetics in the exam, which might as well happen. Don't know yet. I would not ask you to plot 3 graphs, because I know that some people find that quite a challenging thing. The phrase in an exam would be, and you see that in past exam papers, demonstrate graphically that the following data describe a reaction that follows a first order reaction, are from a first order reaction. That could be, and then you get your data. Instruction is clear. What do you know? What order is it? Again, Britney Spears, you don't have to be a rocket surgeon, right? It says it's a first order. So please don't try to convince me that it's not a zero order. I know that, you know that. I know that you know. So the way you would address that is, aha, I know it's a first order reaction, so what do I plot for a first order reaction? I plot Ln of the concentration, natural logarithm of the concentration versus time. I get a straight line. Because it is a straight line, when I plot that, I know it is a first order reaction. It can't be anything else, it must be a first order reaction. 40% of your exam in the bank, if your plot is nice. Make sense? It doesn't get any easier. I could ask you, demonstrate graphically that this is a second order reaction of that particular type. You don't have to try a 0 and see that it's not working. You don't have to try a first and see that it's not working. You just go straight in and say, if it is a second order, I plot 1 over concentration versus time. Give me a straight line. Hey, bingo. Job done. 40% is mine. Happy with that? Shall we go home? I see you next week, bright-eyed and bushy-tailed. Thank you.